Good evening, everyone. Let's wait for a couple of minutes for everyone to join. After that, we will start. Yeah, so let's start with the session. Yeah, so good evening, everyone. It's the 10th live session for the course Basic Environmental Basic for the course Physico-Chemical Process for Wastewater Treatment. Yeah, so during this week, we will be discussing on the advanced oxidation processes and its application for how they are applied for wastewater treatment along with the mechanisms involved in the process. Yeah, so what are advanced oxidation processes? These processes are nothing but tertiary treatment process which are used for the treatment of wastewater, and these are basically used for degradation of organic compounds, like that is the major aim. And the organic compounds which are not degraded in the biological process treatment process, those are generally non-biodegradable compounds, and in that case we use advanced oxidation process to degrade those, because since they are non-biodegradable, you need some strong oxidizing agents that can help in degradation of those organics. Now these type of organics include pharmaceuticals, then we have pesticides, insecticides. There are various more, but these are major. So when these type of compounds they are present in wastewater, they usually don't get degraded by biological treatment process. So here we utilize some strong oxidizing agents, and these are nothing but um, mainly radicals, right? So what are radicals? Radicals are nothing but uh, species with one unpaired electron present, right? So when there is one unpaired electron, it is highly unstable because it has a very high tendency to accept one more electron so that its orbital is complete, and that is why it's very reactive and very short lived. So it immediately tries to react with the compounds there that are present so that it can complete, it can pair the electron, right? So they are further very short lived. So uh, now we are utilizing this reactiveness and its instability to oxidize other compounds, right? So basically what we will be doing in this advanced oxidation process, we will try to generate hydroxyl radical to oxidize uh, organic compounds. Now why only hydroxyl radicals? Because the amount, like the oxidation tendency or the power of any oxidizing agent, it depends on the redox potential, right? So higher the redox potential, you will have better reactivity or better tendency for the oxidation to take place. So here it's the list of a few oxidizing or very common oxidizing agent that can be used. So, and their corresponding redox potential are also mentioned. So here, one of the important oxidizing agent you see from the redox potential is hydroxyl radical, right? So we try to generate hydroxyl radical, and there are few more oxidizing agents also, including hydrogen peroxide, hydroperoxyl radical, ozone, which we will be utilizing in some or the other form, so that we can have uh, the radical formation to oxidize the organics. Now, if you see how hydroxyl radical is formed, then you see O2, like if O2 is present, then it can accept one electron to form the species, which is superoxide anion, and this can further form H2O2. Now, H plus is always available in water, which makes this reaction possible. And again, this H plus H2O2 can further form two hydroxyl radicals by accepting one electron and H plus ion in the presence of these, right? So now this OH radical can react with the organics, right? So basically it will be a chain reaction. Okay, so yeah, so the chain reaction will be such that this OH radical will be reacting with the organic molecules. So organics, actually the reaction is very complex, but if you write in a very short or generalized form, then let's say you have one radical, then it can form intermediate and some another radical, right? So or some another byproduct. Then this intermediate again is very reactive in nature, so this intermediate can again react with some either radical, or it can undergo decomposition on its own. So since we want to oxidize organics, our end product should be CO2, because CO2 is the final, or the it contains the product which cannot be further oxidized, right? So this is the final product after oxidation. So the oxidation will take place until CO2 is formed. So intermediate will go on degradation until CO2 is formed, and at the end we will have radical again. Okay, so this we can further use up. Now there are different ways of generating yes, everyone is okay. Yeah, so there are different the advanced oxidation process is a class of process, and under this there are multiple types of process which works on this principle, where you utilize some or the other oxidizing agent to degrade organics, right? So these type of advanced oxidation process includes photocatalysis, penton based process, electrochemical process, ozone based sonolysis, etc. And the advantage of this process includes they have very high reaction rates, because the main reagent involved here are, you are trying to utilize radicals, and since they are very short lived, they try to react very immediately, making the reactions very fast. Then usually In some or the other form, let's say if you talk about membrane process, then you have two streams. One is permeate stream and another is reject stream. So now this reject stream is highly concentrated because you have not degraded any of the pollutant. You are just trying to recover pure water out of the wastewater treatment, right? Now if you talk about adsorption, then again you will be generating pollutant adsorbed on the adsorbent, and that and like the used adsorbent at the end you need to somewhere send it to or dispose of in the landfill sites. So that is nothing but generation of secondary pollution, right? So you are generating clean water, but at the end you are having some uh, secondary pollution in some other form. So here you can say, since wastewater is like the pollutants or the organics, they are converted into completely CO2, there is no secondary pollution. Like this can be the ideal statement, but if you talk about the real scenario, then CO2 again is an issue because it's a greenhouse gas, right? So if you keep on generating more and more CO2, it can end up with more global warming. So this is like this statement is, you can say, partially correct. And next advantage is this process is very non-selective in nature, because the radicals that you are using, they are since very reactive, it can react with any of the pollutant or any of the organics irrespective of their uh, nature or the characteristic or the type of organics. So basically it's highly non-selective in nature. Yes, and as I've mentioned that they can treat a variety of non-biodegradable organics, and it's specifically used for non-biodegradable organics. Uh, now, this treatment process is mainly used in your wastewater stream, right? So, for example, as biodegradable, if the amount of if the ratio of BOD 8, if it's more than this, then it's, you can say the amount of biodegradable is much higher, right? So out of all the entire COD, the biodegradable component is much higher, right? So you can term this as biodegradable, and you can achieve all sort of major degradation through biological process only. But if it's like the BOD to COD ratio is very low, let's say you have BOD to COD 0.3 or 0.4, then you need to use some process, including advanced oxidation process, for the oxidation of non-biodegradable organics. Yeah, let's move forward and let's discuss each of the uh, type of advanced oxidation process. So first is, let's say, photocatalysis. Now here, if you split up the term photocatalysis, then photo means photon and catalyst is nothing but any substance that enhances the reaction rate, right? So here the reaction takes place in the presence of photon, and what's the purpose of using photon or light is the further enhancement of catalyst activity. Or photocatalysts are nothing but the catalysts which are active under the presence of light only, right? So here, just a second. Yeah, so sorry I got disconnected from the Google Meet. So please wait in case of I get disconnected in between. I will rejoin. Yeah, so we have been discussing on photocatalysis, and here it means that photocatalysis is nothing but catalysts which can change the rate of reaction only in the presence of light, right? So you need the presence of light, and basically you can say photocatalysts are nothing but semiconductors. Why semiconductors? So basically what happens is you utilize the band gap of semiconductors or the uh, catalyst such that electron hole pair is formed upon excitation or upon incidence of light, right? So since conductor have very merged, they have merged valence and conduction band, while the for the insulators the conduction and valence band, they have very high difference in the energy, which means they have very high band gap. So band gap is nothing but difference in the energies of conduction band, the valence band. So since uh, like for insulators you will not be able to excite, or you will not be able to excite the material by light in normal conditions. So semiconductors are the best uh, materials to be used. So they are utilized because they have appropriate band gap that can be easily utilized. Now here what happens is there are multiple reactions. So how do you find out first the band gap, right? So uh, band gap is nothing but the difference between the energies of conduction and valence band. So for that you take like you get the spectrum for this like energy, right? So when you have a plot of alpha is the absorption coefficient and multiplied by the photon energy versus this energy, so in that case you will have such steep, or depending on the material you will get some plot. So this is the linear region of your plot or the spectrum. So when you try to basically it's y equals to mx plus c sort of equation that you will, like the equation which has been shown to you in the class. I have not mentioned it here. So basically what you are doing, you are finding out the intercept, right? So that intercept is obtained by the intersection of the, so when you extrapolate this linear region, whether it's very steep or whether it's slightly slanting, so you extrapolate that linear region up to the x-axis to find the band gap, right? So that will give you directly the band gap. Now, if you talk about different materials, then different materials have different band gap, and depending on the light source or the like more the band gap, more amount of energy you will need to provide. So you try to optimize or try to have an optimum band gap. So what reactions take place when you use these photocatalysis? So, and why is it an advanced oxidation process? So basically uh, when the light is incident on the photocatalyst, holes are formed in the valence band as the electrons get transferred to the conduction band, right? So electron hole pair is formed. Now when this electron hole pair is formed, they are so reactive. So let's take an example of TiO2, which is a well-known semiconductor or a photocatalyst, right? So when the light or photon is incident, electron in the conduction band is formed and a hole in valence band is formed, right? So this hole has the tendency to react with water, which is like readily available in the wastewater stream, to form H plus and OH radical. And as you know, this OH radical is an oxidizing agent that can further react with organic compounds to form degraded products. And if you talk about holes, then it utilizes OH minus present in water to form again the OH radical, right? So basically by generating the OH, the electron and hole pair, you are like at both the bands, conduction and valence band, you are trying to generate radicals that at the end go into the bulk water stream and you degrade the organic products, right? So that is why photocatalysis is known as an advanced oxidation process. And this method is nothing but by various means you are generating radicals, right? So depending on the way you are generating radical, the name of the advanced oxidation process is decided. So since here you are using photocatalysts, the name of this process is photocatalysis, right? And again, the photocatalysis, depending on the phase you are using, it can be divided into two classes: homogeneous and heterogeneous. Or basically it can apply to normally any catalysis process. So any process which involves same phase reaction, so both catalyst and the reactant, which are nothing but the organic compounds. Since organic compounds, they are in liquid phase, so catalyst will also be in liquid phase. So since, or aqueous phase you can say. So if they both are in the same phase, you can term it as homogeneous, because homogeneous here means same, right? So since here we are talking about phase, so homogeneous means same phase. While if you talk about heterogeneous phase, it involves multiple phases, right? And majorly if you talk about catalyst and heterogeneous catalysis, then catalyst will be in solid phase and reactant here will be in aqueous phase, right, or water stream, right? So which means that the organics here are dissolved in water, and solid catalysts, they are present across the wastewater stream. And depending on the catalyst size, you can design or you can choose your uh, reactor uh, type, right? So you can have different types of reactors. Yeah, next is a Fenton process. Again, here we are using some another way of generating radicals, right? So here what we are doing, we are using iron and hydrogen peroxide to generate radicals. So uh, how are this used, and how do how is the radical generated? So here if you see, Fe2 plus is uh, usually added. Fe2 plus and H2O2, they are usually added. Now here if the reaction takes place, then Fe2 plus reacts with peroxide to form Fe3 plus and one radical like hydroxyl radical. Again this hydroxyl radical reacts with H2O2 to form Fe3 plus and another radical, and at the end this Fe3 plus converts into Fe2 plus, right? Like so basically it's a cyclic process where you are utilizing 2 moles of peroxide to generate radicals, and which in turn degrade the products, right? So in general you see that whatever the amount of Fe2 plus, first it gets oxidized and later it gets reduced back to Fe2 plus. So ideally you should not be required to add Fe2 plus, but that is not the scenario, right? So what happens here is, to maintain iron in its aqueous form, or to maintain Fe2 plus in aqueous form, you need acidic medium, or basically Fe3 plus has very low solubility in water, in or it has very low solubility in wastewater depending on the conditions. So it immediately turns into Fe like ferric hydroxides, and these hydroxides are formed very immediately because Fe3 plus is has very low solubility in, or it is soluble in a very narrow range of pH. So it is very important to maintain the pH uh, throughout your process, otherwise the chances of Fe3 plus precipitation increases. So at the end this process generates sludge, and you need to add more and more Fe2 plus during the process. Now any process, advanced oxidation process, you can enhance its efficiency when the process is combined with external UV source or electric supply or ultrasound, which is son sonolysis, right? So you you can have sonocatalysis, sonophotocalysis, sonofenton process, electrofenton process, UV fenton UV process. So you can combine two processes to enhance the effectiveness, right? So that is how it works. And again, you can have homogeneous Fenton process or heterogeneous Fenton process depending on the iron that you are using in aqueous or in solid phase. And in solid phase it will be in the form of oxides or iron metal, and basically it will be the catalyst that you can use for the process to take place. Then you can have, as I mentioned, electrofenton process, which means you are supplying electricity for the Fenton process to occur or to enhance the process efficiency, right? So uh, electricity means you will have an electrolytic or a chemical cell that generates electricity because of the presence of anode and cathode, and the reaction takes place at anode and cathode, right? So what you can look into this schematic. So as the current passes, there are chances that the oxygen which is present by bubbling the air, it gets converted into H2O2 by the reaction at cathode. Again, if you at anode, this H2O2 can get converted into hydroxyl radical, and you can add you know uh, Fe2 plus, which gets converted into Fe3 plus through oxidation at the electrode, and again it can combine with H2O2 to um, you know to form Fe3 plus and the radical, right? So there will be multiple ways of radical generation, which means you are enhancing the efficiency for radical formation, and hence the en- the efficiency of the process is enhanced. Sorry. Uh, Next is the sonofenton process, which means you are passing ultrasound to generate H2O2, right? So in the presence of ultrasound, the water has tendency to form H2O2, which in turn forms a hydroxyl radical, and yeah, the Fenton process takes place, right? So you are utilizing the energies to form H2O. Next is ozonolysis or ozone treatment process. Now, ozone can have multiple application in terms of wastewater. It can be used for disinfection or oxidation of organics, because again, ozone has very high oxidation potential, and it uh, reacts with the microbes to make them inactive in water, right? So if they are made inactive, the chances of further reproduction and further growth of microbes, it reduces, and hence it causes disinfection of water. So these are the reactions that usually take place when ozone is present in water for the ozone treatment. And basically, again, when you are using ozone, you are trying to generate hydroxyl radical. And so since ozone has like three oxygen atoms, makes it very like, and it has a resonating structure, which causes it immediately react to form, through this reactions, it forms hydroxyl radical. Again, as mentioned, you can have ozone combined with UV, or you can externally add H2O2 as well, so that you can enhance the process. So if we talk about UV ozone or ozone UV, then here what happens is, uh, in the presence of UV, this type of species form, which are very, these are nascent oxygen species, and this nascent oxygen species, they are very reactive to form, to react and oxidize the organics. And last is chemical catalytic wet peroxidation, peroxide oxidation, right? So before that, do you have any doubts so far?
Yes.
Yes.
What we have to do also. catalytic wet peroxidation.
Yes, someone is speaking. Can you speak a bit louder? Okay, so catalytic wet peroxidation method is nothing but you are using heterogeneous photon process where solid catalyst which is not soluble in water, so they are used as catalyst, and they further it can be iron based catalyst or some other catalyst that promote so it can be iron oxides, iron uh, nanoparticles that promote the oxidation like Fenton process. Right, so moving forward, next is the electrochemical technology. And electrochemical technology, as the name suggests, it uses the electricity for the treatment of water. And basically, it this electrochemical process is applied applied to have three types of process: coagulation, oxidation, and flotation, depending on what anode cathode you are using, what type of wastewater you have, and what type of um, conditions you have maintained, right? So, or extra reagents if required, you have provided. So, let's talk about first the electrocoagulation. So, electrocoagulation is nothing but you are trying to coagulate the suspended particles, and here the coagulant is generated in situ in the process. So you are using uh, anode as the metal, right? So anode will be pure metal. It can be aluminum based or it can be iron based depending on the coagulant which you want to target, right? So let's say you are, so basically this reaction will take place. So metal which is present at the anode, it reacts with, so it gets oxidized to form Mn plus, right? And this electron obviously generates electricity. Now again at cathode the reduction takes place, right? So H2O can form H2, and this Mn plus which is formed, it can further combine to form uh, further combine with OH minus which is present in water to form hydroxides, right? So these hydroxides, they are nothing but the coagulants which uh, combine with the suspended particles to neutralize its charge and form the bigger particles that can settle easily, right? So this is the basic mechanism behind it. And since it is like you are generating coagulant in situ, so basically it depends on the electrolyte conditions, it depends on the amount of charge formed and the amount of charge utilized in generating electricity and in oxidation. So these are the formula for current efficiency, where you are trying to calculate the efficiency of the process by the amount of, you know, uh, charge utilized per unit total charge, right? And also the anode will keep on degrading and the mass of metal dissolved, it can be calculated by this formula, right? And after some time you need to have a replacement of the anode because you are utilizing basically the material to form coagulant. And the factors that affect the process include the anode which material which you are using, right? So you will not just have one cell, you will have multiple cells in series or some different schematic or design of cell. So the distance between anodes, the water flow rate, and the composition, temperature, pH, all these conditions, they define the the process efficiency. Is it clear so far?
Yes, ma'am.
Okay, so let's move forward. Just a minute. So here, next we will be talking about electrooxidation. So as the name suggests, electrooxidation is nothing but you are trying to oxidize uh, organics and in the presence of electricity or in an electric cell, right? So electrochemical cell. Uh, Basically, what will happen is at the anode or at the electrode, you can have two conditions. One is direct oxidation, where when the pollutant it absorbs on the electrode, and since the electrode has itself the tendency to oxidize, the pollutant gets directly oxidized to the final products. And otherwise, you can have, if you have some catalyst or depending on the anode material, let's say you have uh, uh, generation of radicals. So you are trying to generate radicals, and these radicals in the bulk, when they interact with pollutants, they convert them into the final oxidized uh, organics, right? So yeah, so this process, it usually offers high efficiency, lower sludge, right? Because you are not uh, unlike Fenton process, you are not utilizing any extra chemicals, right? So lower sludge production. And last electrochemical processes for flotation, right? So what happens here is you are trying to generate during an electrochemical reaction, gaseous molecules will be generated at anode and cathode in the form of O2 and H2, right? So these generate micro bubbles of H2 and O2, and when these gas bubbles are formed due to their lower density, they try to move upwards, right, in the cell. And as they move upwards, these gaseous molecules, they tend to take up, since they are in the bubble form, these bubbles um, cause the suspended particles to stick to it, or they carry the suspended particles or oil or grease to the upper layer, right? So it takes to the surface. And since, like, let's say oil if you talk about, or grease you talk about, they have mostly lower density as compared to water, so they will stay there, right? But they were earlier dispersed in water because of the emulsion formation. So now they are, when they are taken up on the surface of water, they will float, and you can use skimmers to scrape off the surface, and you can take off the uh, the pollutants or suspended particles, oil, which have been collected on the surface of water, right? So now let's move for the assignment. So the first question is, what denotes the dot after the radical species in the outer orbital of the molecule? the correct answer to this should be an unpaired electron, right? So it has an unpaired electron, which makes it very unstable and reactive, right? Next is, which of the following is not a highly reactive oxygen species generated in advanced oxidation process? So usually you are using radicals or oxidizing agent, and if you look into the options, hydroxyl radical is the most utilized one. Peroxide is also an oxidizing agent, and this superoxide is also a radical which can be used as oxidizing agent. And NOH is not an oxidizing agent, is a base. So NaOH is the answer for this question. Next is, which of the following is possible when redox level of the substrate is higher than the conduction band and lower than the valence band of the semiconductor? So depending on the oxidation on the levels of conduction band and the valence band, the reactions are possible, and depending on the levels. So here, if this is the condition where you have redox level of the substrate higher than the conduction band and lower than the valence band, neither oxidation nor reduction is possible, right? Next is, the ratio of charge used for the oxidation of compound to the total charge passed during electrolysis is known as dash. So this is the way you are determining the efficiency of electrochemical process, right? By taking the ratio of charge used for oxidation of compound to the total charge, right, passed in an electrochemical cell. So that is nothing but current efficiency.
Current efficiency.
Yes, correct. So next question is, dash is the phenomenon in which an electron hole pair is generated on exposure of semiconducting material to light. So the answer to this question should be,
Electrolyte catalysis.
yeah, photocatalysis. Correct. Next is, the energy difference between valence band and conduction band is known as the band gap.
Band gap.
Yeah, correct. What is possible when the redox level of substrate is lower than the conduction band and higher than the valence band?
Neither oxidation.
Both oxidation and reduction. Okay. So you can look into all these classes when, like, all the possibilities when only oxidation, only reduction, or both or neither can be taking place depending on the levels, right? Next question is, which among the following is the peroxon process? So here you can split the word. So the strategy should be, peroxon means peroxide
O3H2O.
plus ozone, right? So it should be O3H2O2. Yeah, correct. Next is, which is not a Fenton reagent. So Fenton reagent should have Fe in it,
Iron.
right? So identify one which does not have iron in it.
O3H2O.
Correct. So option A, O3H2O2. Next is, and the last one, dash is a process in which buoyant gas bubbles generated during electrolysis take along with them the pollutant materials to the surface of liquid body. It
Electrofloating.
is, yeah, correct. So that is electroflotation, where you are removing the oil, suspended particles, grease, etc. Right? So that's it from my side today. If you have any more doubts, you can do let me know. I will be
Oh,
around here for some time. So you can come up with your thoughts if you have any.
Madam, for the treatment, for the effluent treatment from sugarcane industries, which type of electrochemical process will be best?
Sugarcane industry, I guess, like you are talking about the oxidation or in general which electrochemical. Because for sugar industry, you don't require any advanced oxidation process because whatever the organics that are generated, they will be biodegradable, right? So,
Yes.
sorry.
Mm.
Yeah, so for uh, sugar industry, you don't need any oxidation process, but
Mm.
like and another process, if you talk about coagulation and flotation, so that depends on the industry, right? Because oil and grease can also leak from, like, if they are not generated from industry or if they are not byproducts, they can leak from any of the pipeline joints, or because grease is applied everywhere, right? So that can leak from um, the joints or any of the maintenance, right? So that depends on the industry, whether you want to opt for normal dissolved air flotation, where you generally blast air from the bottom so that it takes up the oil and grease, or you want to have electro flotation. And yeah, coagulation and flocculation, they are always used in any process, right, to remove the suspended particles. But again, it's an option to the industry. It's up to industry what they want to use. So depending on the availability and all, they choose out of all the processes available.
Mm. Okay. Thank you.
Okay. Uh, Good evening. So, actually, I have already discussed on the assignment. So, if you have any doubts, like apart from assignment, like the previous one, or other doubts from the class, you can do let me know.
Good evening, ma'am. Ma'am, can I ask the related problem with the exams?
Yes, sure.
Ma'am, there will be how many questions? 100 or 75?
Actually, we are also TAs, right? So, usually professor sets the question paper. We are not aware of this thing. Sorry.
Okay, ma'am. Thank you, ma'am. Okay, it's creating the confusion. Either it will be of 75 marks or it will be 100 and it will be count in 75 percentage.
I will try to know this, and if I get to know this, I will do let you know in the next class.
Yeah, ma'am, please. It will be beneficial for us.
Sure.
And ma'am, we have received the mail that there will be the multiple choice questions, fill in the blanks, and essay types question. So that is not for the us now. That essay type questions.
It will be for all, right? So
Sorry, ma'am.
questions will be for all, right? So us means what?
Ma'am, in email there is essay type. मतलब shorts answer is also written. So there will be the shorts answer also.
So basically, majorly you will expect the ones which are like similar to the assignment questions, right? So some short questions or short answer or multiple choice, similar questions you can expect.
Okay, ma'am. Thank you so much, ma'am.
Okay. So if there are no more doubts, I will end this class for today. Thank you everyone for joining.